The first law of thermodynamics states that energy is always conserved. So, if you know where most of your energy went or where it came from, you can find what energy remains and where it went. Energy comes in two basic forms as far as we're concerned: thermal and physical energy. Thermal energy is temperature related or temperature driven, while physical energy is from physical phenomena such as the movement of particles, the work done by a system. It's the application of forces to deposit energy. System energy is a combination of the two, but held by the mass in our system within our controlled volume. Typically, we will describe the total system energy with enthalpy, which is a combination of the internal thermal energy and the physical boundary energy that contains that working fluid. And that's where we get the equation enthalpy equals internal energy plus PV, or H equals U plus PV. The second law of thermodynamics is all about the flow of energy. It states that 100% efficiency is impossible, since at least some energy will leak to the lower energy reservoir. Energy flows from high potential to low potential. The bigger the difference in potential, the stronger the flow, and this means for a heat engine, a wider temperature range allows for higher efficiency since that flow is much stronger. However, a refrigerator or heat pump is going to struggle because it is trying to oppose that flow. Based on the second law of thermodynamics, we can make some interesting assumptions, and this is where we get into ideal heat engines and heat pumps and refrigerators. Heat flow is determined by temperature. So for an ideal system, we can use the temperatures of the heat reservoirs as our stand-ins for heat. This is based on the assumption that our heat flow will be directly proportional to the temperature difference. For real devices, however, our results will be worse due to the losses and inefficiencies within the actual real system. So we'll need to use heat to do our calculations for real systems. The reason we were taught how to do ideal calculations or ideal systems is because that is the theoretical best. If somebody says, hey, I've got a car engine that does 90% efficiency, you already know that's kind of BS, because that's well beyond what a Carnot engine would be able to do. So that's the reason why we learn about these ideal systems. It's a sanity check. It's a matter of seeing if something is even remotely possible to begin with. Now, there's a number of devices that use the properties we've learned so far to change the conditions of our working fluid in our systems. Nozzles and diffusers affect the fluid dynamic properties we learned about earlier in the class by constricting or widening the flow path. Constricting flow increases flow velocity and reduces pressure, and diffusers do the opposite. They widen the cross-sectional area, causing the fluid to slow down and increase in pressure. We assume no change in temperature, no heat flow, and no work done by the nozzles or diffusers. Pumps, compressors, and fans add work energy to a fluid. We assume there's no heat flow or heat loss, and turbines do the opposite of what a pump or a compressor will do. They extract work energy from the motion of a fluid. Compressors will specifically change the volume of a fluid, hence they compress something. So typically this will be a supercritical fluid or an actual gas of some kind being compressed down and sometimes pushed into a liquid form. Pumps will usually take a non-compressible fluid and simply move it. A heat exchanger allows for heat flow between two fluids while keeping both of them physically isolated from each other. In this type of device, there is no work done and no heat flow from outside the system boundary, but there is another source of energy, the fluids themselves. This is the system energy. We have two systems that are able to pass heat between each other. They both have enthalpy and internal energy, and since we presume they have different temperatures, energy will flow from the enthalpy of one fluid into the other, following the temperature gradient. The hot fluid will give up energy to the colder fluid. A mixing chamber lets enthalpy exchange between multiple fluids, but unlike a heat exchanger, it does so by actually mixing those fluids together. If you've ever put ice in a hot drink, you've made a mixing chamber. There's no external work and no external heat, so all of the energy comes from the enthalpies of the fluids. A pipe or a duct by itself doesn't really do anything, but we can put something in that pipe that can do work to the fluid, such as an electric heater or a paddle wheel. We can also put our next device, a throttling valve, inside a pipe. Throttling valves are isenthalpic devices, meaning the enthalpy of the fluid doesn't change. That seems kind of pointless at first, but remember that enthalpy is a combination of our two energy types, physical and thermal. A throttling valve can cause the pressure and volume relationship of a fluid to change when traveling across it, like, say, causing a fluid to boil or evaporate. If the physical energy increases, the internal energy decreases, and since internal energy is thermal energy, meaning it's temperature-driven or temperature-related, the fluid will cool down. That makes it really useful for something like a heat pump. In a heat pump, a throttling valve is used to make the refrigerant boil at a low temperature by increasing its specific volume and lowering the pressure. This lowers the internal energy of the fluid, which means lower temperatures. When this boiled refrigerant gets to the first heat exchanger, called the evaporator, heat flows into the fluid, which is then carried to the compressor. The compressor undoes what the throttling valve does. It forces the fluid back into a liquid state, causing it to give up energy, which is then dumped through a second heat exchanger, which we call the condenser.